In this video, we're going to illustrate how spherical geometry forms the basis for the coordinate systems we use in geolocation and surface navigation. While the Earth isn't perfectly round, it is close enough so that we can get away with using a spherical model for navigational purposes. Now, here's our planet Earth. We have our rotational axis here, and this is what creates our north and south poles at the ends. We're going to slice our sphere with a plane, and that plane is going to intersect the middle, the geographic center. The result is what we call a great circle. This is the maximum circle size that you can draw on the surface of a sphere. When we make our slice, we're also left with two volumetrically identical pieces of the sphere itself. Those are called hemispheres. Let's consider just a segment of our great circle. This is what we call a great arc, and it represents the shortest distance between any 2 points on our spherical surface. In future videos, when we take a look at both site reduction and great circle sailing, great arcs are going to be a big part of that, and they're the result of taking spherical geometry and applying spherical trigonometry, a little mathematical computation. In addition to great circles, we also have another important type of circle, and this one is created when we have our intersecting plane that does not pass through the center of the sphere. This is called a small circle. In addition to being on a plane that is off-center, the small circle has a smaller size, smaller diameter, and a smaller circumference than the great circles do. Let's take a look at our model and add some great circles that intersect our poles, North Pole and South Pole, along the axis of rotation. It's going to look kind of like a spinning coin. This is the building block for what we call a meridian. We're going to isolate one of these circles, and we're going to pick a position, a point that's somewhere along the circle. Now, the polar axis is going to split this great circle and create two opposite sides of the planet. The one without our position on it, we'll call this the dark side, that's called the lower branch. The opposite side with our position is the upper branch, aka meridian. Now, we use the word meridian most often because we don't really deal with the lower branch all that often. The most important meridian on Earth is the prime meridian. This is the great arc that passes through Greenwich Observatory in London, and it's the reference plane from which all other meridian are measured. Now, a meridian gets its value because it helps us define a position on Earth based on its angular distance from the prime meridian. This angular distance is called longitude, and it's measured in degrees. If we look down at the Earth from the North Pole, we get a vantage point that helps us understand the prime meridian here, which represents 0 degrees longitude, and the anti-meridian, which represents 180 degrees longitude. That's the opposite side of the Earth. The combination of these meridians creates two equal but opposite hemispheres, the Western Hemisphere and the Eastern Hemisphere. When we measure longitude, the designation east or west is added to the angle to indicate the direction and hemisphere. Let's assume we have a position in the west and a corresponding meridian. The shaded region that's purple here represents the measurement of longitude in degrees west. While in the eastern hemisphere, if we assume the same setup, we have a position with a corresponding meridian, and we are measuring longitude in degrees east. Meridians and longitude together make up half of the coordinate system that we use to navigate the Earth. Let's take a look at the other half. We're going to start with a counterpart to the prime meridian, which is a great circle that is perpendicular to the polar axis. This is the equator, and it's the reference plane that we use to measure angles latitude. And just as before with east and west, we now have a division between north and south. So the equator conveniently divides the Earth into a north hemisphere and a south hemisphere. Latitude is an interior angle, and it's measured between a position on the Earth's surface and the plane of the equator with the center of Earth as vertex. The yellow shaded region here shows the angle of latitude. And as with our longitude measurements, latitude is also designated north or south depending on the direction and hemisphere. Latitude measurements begin at 0 degrees from the equator and can go as high as 90 degrees at the poles where they terminate. If you connected all the surface positions with the same latitude, you would have a circle that runs parallel to the equator. This is what is called a parallel, and it represents a line of equal latitude. Except for the equator and the 2 points at the poles themselves, all parallels are small circles. You can kind of imagine parallels as stacking up one on top of each other from the South Pole to the North Pole, kind of looking like different sized plates. Let's add our meridians back in with our parallel model. When you see these and use them together, we can define any position on the Earth as the intersection of a meridian and a parallel, with a corresponding latitude and longitude value. And this forms the basis of our navigational coordinate system. Just remember to include the correct hemispheres, that designation north-south and east-west. If you screw those up or omit those, you're probably going to be off track by several orders of magnitude. So that's going to wrap it up for the coordinate system. In future videos, we're going to take a look at the terrestrial coordinates a little bit more, and we're going to move on to the celestial sphere and celestial coordinates and how we determine those. Thanks for checking us out at Oceans Unlimited. If you found this video helpful, please consider leaving a like or throwing a comment down below to help us grow the channel. Also, be sure to subscribe if you have license exams coming up, or if you're just looking for some tips and tricks. See you next time.